can catch up. Anybody who's having internet trouble can go back, and anybody who wants to see again what we covered. And I'm going to send you around an email shortly, which just shows you where you can find that in Moodle, the learning management system, so you can find that. And also, I'm going to be sending you shortly your assignment for the end of this session, where you actually have to do a little something based on Evan's discussion of road safety barriers and products. And you'll have to do a little bit of work, but it'll only take you 10 to 15 minutes most. It's not a hard exercise. You'll also have a quiz. Thank you for those who did the quiz. Those who haven't done last module's quiz, get in there and do it. Most of you got through there with quite high marks. Right, let me introduce Evan. Evan Coulson from the Department of Transport in Victoria, but also sits on ASBAP, the Off-Road Safety Barrier Assessment Panel, and has been heavily involved in barriers for quite a while now, and someone who's very passionate about us getting it as right as we can. So we've asked Evan to come along to talk to you about a variety of things associated with the acceptance of systems and the hoops they have to jump through to get a product on the network, and some of those products and their features. So I'm going to be in the background collecting questions for Evan as we go, and I'll jump in occasionally and maybe ask the group questions or the like, but please do pop those questions into the Q&A as you think of them, and then at appropriate points I'll ask Evan those questions. So keep them coming in, and over to you, Evan.
No worries. Thank you, Ken. I will share my screen now. Screen share. Alrighty. And then let's get into presentation mode. Alrighty, hopefully everyone can see that. So I've got 4 presentations, all of different lengths, but basically I'll be going over the acceptance process, what it takes to get a product from an idea to on the accepted list so that someone can use it during the design and installation. I'll then go into how we test, how we evaluate those products during the acceptance process. And then after that, we'll get into some permanent barriers, all the different types and some key features of those, and then a bit into temporary barriers at the very end. So I do use up sort of the full 2 hours, so I apologize if I feel like I'm rushing, but hopefully I guess that it leaves a little bit of that question time in between, which I think is more useful. So as I said, how does it go from an idea to a list of accepted products? Now, this is generally the process. A supplier, normally someone out in the private industry, has an idea. They will develop it, check the feasibility of it. They will invest heavily in this process. They will then crash test the product. So all of this happens generally by a private company. There's generally some intellectual property with it. They go away and crash test, and they package everything up and they submit it to ASBAP and then to the specific road authorities. So I'm going to talk about sort of these last 2 here mainly. So the first one, ASBAP, the Off-Road Safety Barrier Assessment Panel. So before this group was put together, each of the road authorities were doing their own assessments. So we're each checking the crash testing, checking the quality of installation, the product, how it goes together, how it could get misused, everything. And we realized it's going to be much more efficient and actually a much more stringent sort of assessment to bring everyone together and do it as a panel. And so the Off-Road Safety Barrier Assessment Panel, ASBAP, consists of someone from each of the road authorities from Australia and New Zealand. And basically we go through and we evaluate each of the new products that get submitted to us. We meet 4 times a year. It used to be more. We found that that's probably the right balance, meaning that if someone submits a product, then it will go to pre-assessment by 1 or 2 of the experts, and then it will come back to the panel. So it can take 6 months to 3 months, depending on when they submitted it, to be fully assessed. But we feel that, when it happens faster, we miss things, and, we all actually have our normal jobs as well to do. So 4 times a year, and it can take anywhere between 3 to 6 months to get a new product approved. Now, actually, I've made my own mistake there. The panel does not approve the use of barrier products. It recommends. What the panel is doing is evaluating the product and saying, yes, it meets all of the assessment criteria. We recommend that state road authorities accept it like this, and we give a set of technical conditions. If a product is not found reasonable, then it's considered not recommended. And the position is that ASBAP is saying to state road authorities, we don't recommend this product for acceptance. And generally there'll be some reason why, because it didn't complete one test or there was some issues with another. More information can be found on the Austroads website. The suppliers put together a pretty big package of information, and they submit it through. And basically what happens after, or at the end of it, if they're successful, a letter is sent to them that says, yes, your product has been recommended for acceptance. Feel free to hand this on to state road authorities. And here is a technical conditions of use, a list of values and criteria that we identified as part of the assessment, and that we think is how the product should be used to make sure it meets that MASH performance. Now, once Austroads is done, and this is a very generic process, but it's fairly similar for each of the states. Once the Austroads assessment is done, so they've handed over a letter to the supplier, then they go and approach the state road authority. So the product or variant is then submitted to the road authority. So that could be DOT, RMS, QTMR. The road authority does their own internal check. Does the product add value? And, there are such things as too many variants of a specific product. And there are also other elements around, Western Australia having very, very regional locations where they just can't attend, sort of within a reasonable time frame, and they need to be able to manage what assets are out on their network. So the state road authority does the product add value on top of what they've already got? Does the product integrate with the local network? What barriers are out there? What connections do we need? What is their general regime of maintenance? Does the state need additional requirements? So each state could add additional requirements. An example of this might be Western Australia giving a larger foundation for a wire road because the soil may be weaker nominally over in Western Australia. Then they might set an additional requirement. There also might be things around who can sign off and who can install these things. So yes, the state road authority can add additional requirements. They'll go through an internal process that could be seeking acceptance from the relevant person internally. And then if it all goes well, the state finally accepts it. So they convert the recommendation from Austroads into an acceptance. They might give the supplier a letter, and ultimately it gets published onto the website so everyone can see and everyone knows exactly which products have been accepted by that state. Excuse me. While national harmonization is what we're aiming for, and which is why, we try to all use the same TCUs and have the least amount of additional requirements possible, it is still important that it goes through these checks. And so it especially in the near future, we won't be hitting a point where all states accept all the exact same products similarly, because we all have legacy issues. We all have different networks that we need to manage.
Evan, do you just want to define the acronym TCU?
TCU, sorry, the technical conditions of use. So when Austroads, if Austroads finds a document recommended for use, it gives the letter and it gives this document over here, sorry, the safety barrier technical conditions of use, TCU. I apologize, and I'll probably keep saying that through, but yeah, TCU just really implies sort of the values and conditions that we think the product is reasonable for.
Thank you.
So I'm realizing this is probably showing up on the screen, so let me get rid of that. Alrighty, so the supplier gets a letter from the relevant road authority. That's an example there from Victoria. They celebrate, and then it goes on to, excuse me, a list. And that list could be in a PDF, like I'm showing here in Victoria, or it could be on a website, like they do in New South Wales. So the list of accepted safety barrier products is shown on the website. They have split it up by permanent, work zone, temporary, terminal, and crash cushions, gates. So they have a couple of separate areas for the different types of products, and we'll go through each of these a bit later. They'll just have a list of the product name and the test level, and basically all of these all of these titles link directly to the TCU, the technical conditions of use, the document that outlines exactly how that product should be used. And so here's the example. Click on Nash TL3 Bryphon, and what will pop up is the RMS acceptance conditions. Now, yes, it's New South Wales branded or RMS branded, but it's very much similar to the Austroads TCU. And it's a similar practice that we're now adopting down in Victoria, is to directly link to the Austroads TCUs. Again, just a bit of saving time and a bit of harmonization benefits. But you've got your full list on the left on the website, and then you can click through to each of them, and you'll get the detailed conditions. So in summary, with acceptance, don't use a product that's not on the accepted list. Even if the manufacturer has it up on the website, it may have gone to Austroads. There may have been, some nuance in the testing where it wasn't pinned correctly, or it wasn't meeting MASH, and it hasn't been accepted. Or they just might have not crash tested it whatsoever and are claiming that, this is the best product that the world's ever seen, and it does this and that. It just needs to go through the process. We need to have, the relevant SMEs looking at it, doing that due diligence. So you really shouldn't be using a product that's not on the accepted list. And if you are, you really need to know that you're taking on that assessment. You're saying, I've assessed it in accordance with AS 3845, and we'll go into the relevant standards next. I find it suitable. And I just don't think, if you're saying, well, I read a manufacturer's website or a supplier's website, that would be a good defense. So don't use it unless it's on the list. Always check the latest list. Don't modify or use the product differently. So we do try to evaluate it in a range of conditions based on what they submit. Pushing it, a little bit beyond, is unfortunately just the reality, and we may need to do that. But modifying the product, will eventually mean that it doesn't perform the way that we accepted it. We will not consider any products that have not gone through the national process. So everyone's on board with this, must go through ASBAP, the Austroads Safety Barrier Assessment Panel, first. And each of the state road authorities can always remove a product if it hasn't been working on site, not necessarily crashworthiness, but it hasn't been installing well. There seems to be maintenance issues or repair issues. And so, products can be removed by the state road authority at any time. Alrighty, well, that is the first presentation, the accepted list. I'll jump over to Ken. Is there any sort of questions that have popped up?
No, nothing yet, Evan.
Right.
So keep motoring along. I think people will have some questions in some of the other.
Yep. No worries. Alrighty, so we now understand, I guess, the process for a product to get on the list. The next part I wanted to talk about is, what is that assessment? What performance are we checking for? What standards are we checking to? what are we actually looking at as part of Austroads, ASBAP, or as part of a state road authority? And this is the bit where I'm going to get into a bit of crash testing and the terms of MASH and 350 and stuff like that. So how do we determine if a product actually redirects and contains a vehicle? Now, hopefully for those that have a good internet connection, or maybe my internet connection's bad, this is a video of some very old crash testing. And it's basically showing a black and white video of a car rolling down a hill and hitting what looks like a wire rope safety barrier, or a couple of posts with some cable joined between it. The principles are really still the same. What vehicle do you roll down the hill? What speed do you try and achieve when you hit the barrier, and what angle? And, you know, they've made those subtle decisions when they crash tested that. Yes, it's pretty, primitive. They've just rolled it down a hill, but they've still made those three key decisions. They've chosen a vehicle type. They've tried to achieve a certain speed, or it could have just been how big the hill was. And they've chosen an angle. They've installed that barrier, that way so that the vehicle would hit it at a certain angle. And that is essentially the main matrix of tests, is a combination of different vehicle sizes, angles, and speed. So where do we get this information from? Now, there have been crash test protocols. So how you crash test a product have been around for a while. However, the names or the initials that you'll know the most are NCHRP 350. So this was a report completed in 1993 to look at, an updated protocol. And finally, MASH, the Manual for Assessing Safety Hardware. And these would be the latest. The first version was out in 2009, and the second version out in 2016, with some minor additions to, wire rope and wire rope on verges. So nothing major, but just trying to, I guess, extend some of those unique installation scenarios. These are the protocols, and these ones here that I'm actually showing are just American ones. And we use these, but we actually need something to bring these all together and say that we use these. Australian standard / New Zealand standard 3845, which is road safety barriers. This is the document that pulls it all together. This document talks about, how to determine if a product or a barrier is suitable. It talks about the testing and how you need to install it and everything that should be evaluated before you accept a product. And we use, or Austroads use, this product, this standard very closely. So our whole evaluation process is set around this, and it does go into a lot of detail. However, it does reference three documents: NCHRP 350, which was that American crash test protocol from the last slide. It references MASH, and it also references the European standard, which is EN 1317. It does call MASH out as the basis. So as the new update in 2015, it says MASH shall be the basis for all testing and evaluation. However, it will consider products that have been tested to these other manuals. Now, why use an American or a European standard? Why not go away and develop one ourselves? Well, the reality was that most of these companies designing or innovating new products are in America and in Europe. That is where the market is much bigger. That is where they see the profit for their investment. And so rather than creating a new protocol, therefore saying to people, you'll have to re-crash test and spend nearly up to $1 million crash testing again, we said we'll adopt the American protocols and the Euro protocols. And the idea being that they could grab the product that they use in America or Europe and bring it to Australia And that way we sort of get that edge on, the latest innovations, the latest products and variants can be easily submitted to Australia. Now, why MASH or European? And we'll get into that a little bit later, but looking at, we talked about the type of vehicle, the type of speed and the type of angle. Our roads and our vehicles actually look a little bit more like America than Europe. Europe generally has smaller cars on average, but higher speeds, whereas MASH, America, larger pickup trucks and vehicles, and most of their highways are similar to us with a 100K posted limit, most of the time, 110 maximum. So we felt that the American standard was more suitable as the basis here in Australia. So the Australian standard MASH shall be the basis of testing procedures. Road safety barrier systems and devices that have been tested to these other protocols can still be evaluated. And acceptance by the US or by Europe or anything like that does not automatically mean that it is accepted here. Most suppliers will pick up the assessment and hand it in as part of their submission and say, has been accepted over here. And we might look at the justification or the way in which they accepted it in the US, but it doesn't automatically mean that it's acceptable because we have a different Australian standard. The FHWA are assessing a product to their standards. They're not saying that it meets AS 3845. And so we really need to make sure that that check is done, which is why Austroads ASBAP has been set up. Why do we crash test? Well, really, we want to understand how or if these products are likely to work in the real world. Now, there are infinite possibilities out on site. Yeah. A range of different vehicle types and sizes and weights, a range of speeds, a range of angles. We can't crash test everything or every scenario. And to that extent, it means that not every product is perfect because it hasn't been tested in every possible scenario. What these protocols do is they set practical worst case scenarios. So they try and set an upper limit. What is the reasonably large vehicle, reasonably large high speed and high angle? And what it also does is that each of the products are tested consistently. So we can have some comparison, we can have some understanding about how concrete works versus wire rope or guard fins because they're being tested in the same way. So the reality is that these protocols set that limit and means that if someone can pass that, then we're pretty comfortable that they can pass a worst practical case. So how do we crash test those three components? Vehicle. Now, how do we pick a vehicle? This diagram up the top, it shows some data from Victoria from a couple of years ago. And I guess it's just useful to highlight, and you'd have similar graphs in other states and probably similar graphs in the US, but this is a graph that shows vehicle weight on the bottom here, so 0 all the way up, and I haven't extended it, and the amount of registered vehicles. Now we can see passenger vehicles dominate the spread of vehicles that are registered in Victoria. I think there was like 4.6 million total registered vehicles, and we're sort of hitting up the peak that this one weight is getting to 1.4 million vehicles around this weight, and so this area makes up the most of it. So with that concept in mind, the first vehicles that we check or we select are the small passenger vehicle, 1,100 kilograms, somewhere down here, and the large passenger vehicle, 270, so somewhere up here. And the idea is that if we test the smallest and the largest, then hopefully we've captured everything inside. And every barrier must be tested with these two vehicle types. small passenger car, and then the large passenger car, normally called a pickup in America. You then go up and there are layers above that, 10 tons, which, sort of all the way up here, hopefully covering all of these. 36 tons is up again. And so they've tried to set these levels where we absolutely always crash test for the passenger vehicles, but if you have greater risk or you have an asset that needs protecting, then we'll develop these protocols that include larger vehicles. So a small car looks something like that. It used to be 820 and now 1100. There's a 0 and an O in there. And the crash test video, if I click that, there we go. Now this one is very much testing for underride or underrun and also occupant risk. So does the vehicle, because it's the small passenger car, go under the barrier, whether that's the rail, whether that's the ropes, and how much or how severe is the impact for occupants? The next one, the large passenger vehicle or SUV. We can see a difference from NCHRP 350 to MASH, taller bumper height, larger weight. And again, this is testing that maximum sort of load from a passenger vehicle. It hits high, it hits with a large amount of energy, and it's the most likely, unless you start going to TL4 and TL5, impact to sort of breach through or overrun the barrier. So hopefully with those two tests, we know about underrun, we know about overrun, and we've also tested for that sort of large impact energy. Once you move above that, we go into the 8-ton or 10-ton now. So TL4 has gone up, and then into the 36 tons. So there is a TL5 and a 6, and I think I'll come back to that in a minute. These are two different tests. So there's the 36-ton trailer truck test, something like this over here on the right. And there's also a level above that, which is a 36-ton tanker. And while their weights are the same, their behavior during impact are different. This one on the bottom right, which is the TL6, the test level 6, and I'll come back into that, has a movable liquid, or I guess back where carry load. And so when it impacts the barrier, it actually behaves quite differently because you get these multiple impacts. You get the front compartment impacting, the second or the back impacting, and then as all that load moves or flows across into it, you get that sort of third very high impact, which is much more likely to tip over a shorter barrier. Whereas I guess for the TL5, because it's all sort of considered one articulated truck, then you're less likely to roll, or you can achieve a redirection with a lower barrier than you can with the TL5. So yes, the weights are the same, but they do perform quite differently. For other than sort of concrete, the only real products that get to TL4 are your Thri-beam and your wire ropes. And the idea being that, you can spread that ropes out, you can spread that contact area around. You're still protecting for the large car, but it's still tall enough to protect for those larger vehicles. And it is one of the big benefits of wire rope, the fact that you can spread it out and capture a range of different vehicle shapes and sizes because of how far apart you can get the top rope and the bottom rope. So it comes back to this drawing, which is a bit of a summary drawing in there. On the left here, test level 1, 2, 3, 4, 5, and I haven't included 6, but it's pretty much the same. On the top, we have the vehicle, small passenger, large passenger, truck, and then the large articulated truck. We pick an angle for each of these, so 25 degrees for the 2 passenger vehicles and slightly lower for the trucks. These angles are based on the protocol, and the protocol is based on crash statistics. So America looked at 4,000 runoff road scenarios, and they found that these angles were, the worst practical cases. Yes, you get some angles that are higher than this, but most, that sort of 85th percentile of runoff roads leave the road at around 25 degrees. So putting those together, TL1, the 2 passenger vehicles at 50. TL2, the same 2 passenger vehicles at 70. TL3, the same 2 passenger vehicles at 100. And this is the most common crash test that people are aiming for. TL4, you still have to do the passenger vehicles at 100, but you add on the 10-ton truck at 90. And TL5, passenger vehicles at 100 and add on the 36-ton at 80. Now, this doesn't mean that you can only use it at 90 k's an hour because it works at 100, or that you can only use it at 80. These are the worst practical cases. America has roads posted at 100 and 110. So they have very, very similar networks to us in that respect, amount of lanes, verges, everything like that. And these are the speeds that these vehicles happen to run off at. So this crash test speed doesn't mean you can only use it on a 90 or 80k road. It just is setting the next level up. And it actually went from 80 in NCHRP 350 to 90 in MASH. So they are finding, okay, we've reevaluated, these 10-ton trucks are coming off at higher speeds. But right now it's all about what test level do you need? And this is how the supplier needs to crash test to prove that it is that test level.
So Evan, why would you ever not go to the highest test level? Why wouldn't you always pick a test level 5?
Yep. And fair question. And it is just about value for money. As we see, you'll need taller and stronger barriers to contain those larger vehicles. And when we talk about TL5 and 6, we only have concrete. And so if we said, we have to have TL5 or 6 everywhere, let's say TL5, then we would burn through the resources that we have much faster. Whereas, I guess if we get that balance right, then we get to utilize our resources more effectively. And so, generally, the approach that most road authorities will take is TL3 is that minimum, is that default. If it's a highway or if there's a large percentage of vehicles or a large volume of vehicles, then they might say, well, it's worth the added cost because generally these barriers will cost more, and they'll ask for a TL4 or they'll ask for a TL5. Or the risk is so severe. If someone went through and collided with that asset or went off a bridge and onto the road below, the result or the consequence is so catastrophic that it actually stacks up to install a TL5 or 6 product because there's still value for money given the risk. So it's really just about trying to utilize the resources you've got and try and protect as much as you can, as reasonably as you can.
Okay, thank you.
This is a good diagram. It shows sort of the energy, the impact energy as it increases. The green is the old standard NCHRP 350 and blue is the new MASH protocol. We can see there's a general increase as you go up from TL1 all the way to 6. As I said, there is the same energy for these, but it's the way that they impact the barrier that is quite different. And the other thing that I just wanted to highlight, I think there is there we go, is the change between TL4, between the 2 protocols. You can see the gradual increase, 1, 2, 3, all of the MASH tests are slightly larger than the 350, but this is the biggest one, TL4. The old NCHRP TL4 had the same energy as TL3. And the idea was that they would test with the same energy, so most of the barriers could contain the energy, but they would check for larger center of gravity. And so it's actually the case that, many products were able to just sort of increase the height a little bit and then pass the TL4, and that's fine. However, I guess I just wanted to highlight that it is very unreasonable to compare a TL4 from 350 with a TL4 from MASH, because it's a huge change. And not only does the energy now increase, so too does the center of gravity. The speed increased from the test, and so did the weight. And so while you may have gotten W-beam systems passing this, there's no way to get a W-beam to pass a TL4. So most TL4 systems these days under MASH are going to be your Thri-beam, your concrete, or potentially wire rope. So wire rope can still contain that if you get the rope spread correct. Now, I talked about longitudinal barriers. So all those tests before about the small vehicle and the large vehicle and the speed and angle is just for the midsection of the barrier. There's a whole new matrix for the terminals. Same principles, small car and large car, straight on, at an angle, at the critical impact point. So the place that creates the highest occupant risk or severity, the length of need, so where that terminal begins to redirect. And I think I'll go into that a bit later throughout these slides. And then on the reverse, which again, if you're going from something that is stiff into a flexible terminal, not an issue, but it's where we go from a flexible barrier into a more rigid terminal that you get this effect called pocketing, where they're coming in, it's deflecting, and they might be dragged into a rigid back. And that could be a crash cushion on a plastic temporary barrier. That combination would just not work, because the plastic barrier deflects and it would be coming in right into the back of that pinned crash cushion. And so that's why that combination isn't accepted, because they just would never be able to pass the test 39. So again, a big matrix of tests for the terminals. And similar with crash cushions, the only real difference here is that it adds in a 20 degree as well. So because these are generally redirective right from the beginning, there is this 20 degree angle impact right on the nose. Whereas in the previous ones, there is an assumption that would just sort of go through the barrier or through the terminal. And so 15 degrees actually has the greater risk being passed on to the occupant, whereas in a crash cushion, 20 would be that worst. So that is the matrix. That is the tests that the supplier has to say, right, I've got my product. Now I've got to pay someone to actually go and crash test this. If it's a barrier, you could get away with 2 tests if you're lucky. But from experience and working with some of the suppliers, no one ever gets it right on their first attempt. And there is a bit of testing, figuring out what happened, how they could make it better. But if you got everything perfect, yes, you could get away with 2 tests for a longitudinal barrier. Whereas if you're doing a crash cushion or a terminal, minimum, 7 tests. What are we looking for in those tests? 3 things. Structural adequacy. Does the barrier actually withstand the impact load? Does it contain or redirect a vehicle? Does it withstand the impact energy and redirect that? The second, occupant risk. Does the driver actually survive, or do the other occupants in the vehicle actually survive? And we measure this using gyroscopes and various instruments throughout the vehicle to make sure, one, the compartment isn't breaking, there aren't any bits spearing into the compartment, the occupant compartment, and also that the occupants will survive the deceleration, the G forces on them when they go from 100 Ks down to whatever their exit speed is. And then finally, post-impact trajectory. Does the vehicle leave the barrier after an impact at a reasonable angle? And I've probably got a note there. What's going on? Preferable that the vehicle trajectory does not enter the adjacent lane. So it obviously has to leave at some angle. You know, can't just have it stop against the barrier. But, you know, we do require that it leaves the barrier at a reasonable angle and isn't likely to head off into the opposing direction or travel lane. So structural adequacy, obviously this one on the left here would be a clear failure, but we're also looking at, you know, is it on the peak or is it on the very brim of a fail? If a crash test was like this, then, you know, it would be questioning, well, is it likely to do that for slightly larger tests? And, you know, yes, the supplier to some extent is designing the cheapest barrier they can to pass the test. That's, you know, what everyone does. We've given them the goalposts and we've made the goalposts fairly hard. And they basically design a system that they believe is they can sell and that is cost effective, that meets those goalposts. But we still do look at how close or how on the bare minimum they've tried to design it. So structural adequacy, occupant risk. This video I think we showed before. Looking for a couple of things. Detached fragments, do they enter the compartment? Does anything spear the compartment? How stable is the vehicle? And also, does the vehicle meet its deceleration rates? And I think there's a diagram in the next one. We test for two things. This occupant impact velocity. So that is when the vehicle first hits the barrier, the occupants are thrusted forward and they'll either hit the dashboard or the steering wheel or the side of the vehicle. So is that survivable in itself? And once they've become part of the vehicle, does the whole vehicle in themselves decelerate at a reasonable rate? And the one thing I wanted to highlight here is we've got these preferreds and we've got these maximums for each. 9 meters per second, 12 meters per second, and 15 Gs and 20 Gs. Yes, there are a difference between the systems, wire rope versus flexible W-beam concrete. So yes, wire rope gets, you know, roughly half of a concrete, and similar with the occupant ride downs, the Gs. However, I just wanted to highlight that we're still well below preferred and maximum. Concrete, you know, we're getting values up around 6, well below preferred, 12 to 14 Gs, still below preferred. So, you know, while yes, it is very true that wire rope is the most forgiving of all of them, it is very unreasonable to say that concrete is dangerous or that it's unsafe, because it's still well below the preferred and maximum. The only time these values really kick in are for terminals and transitions, because we're bringing the vehicle to a stop very quickly. And those values will generally get up around the 15 to 20. But longitudinal barriers, you know, we're really still below the values that we're looking for. And this doesn't mean automatically someone's injured, or less than this, automatically no one's injured. It gives these values where impacts with a deceleration of less than 15 is unlikely to injure someone, whereas above 15 or above 20 is more likely to injure someone. So it's still possible, but I guess it sets some fairly practical levels. The exit box, I won't get too much into detail like this, but the crash test house where they went and crash tested will have cameras everywhere, and they'll need to digitally sort of record this based on the impact angle and where it left the barrier. They draw sort of this virtual box and make sure that it leaves within that A side of the block. I've got some videos here. I guess the one doesn't really add much. The one challenge with post trajectory is that when we crash test, we're simulating that someone's let go of the steering wheel. And they don't brake yet. They brake around 2 seconds after they leave the barrier. So we've seen the post trajectory, where it goes after. But in the field, often what happens is someone will impact the barrier and then they'll naturally turn the steering wheel as far right as possible. And that's going to create this post trajectory, not because the barrier has really caused it, but because that combination of the driver hitting it, turning their steering wheel. And I will admit that is something that's a bit of a gap. A lot of, reports will come in and say the barrier has bounced someone away. And by all means, it does look like that. You can see the tire marks, the steering is fully turned to the right and they've flown off away from the barrier. It is very hard, I guess, to be able to test for that. All the protocols sort of earlier in 2 data are really just assuming the driver has let go. They're impacting the barrier without any sort of intervention until they've left the barrier. They can slam on the brakes and bring the vehicle to a stop. But yeah, I guess by all intents and purposes for the crash test protocol, there is that post trajectory requirement. And so basically, once everything we learn from that goes into these TCUs, these technical conditions of use, we will list the test levels that were achieved, MASH TL4 or MASH TL3. We will show the minimum length of barrier that was tested, the deflection and the working widths. We will explain or detail the terminals that were used, some of the additional requirements, and even the pavement conditions. If it's a product where you drive the post into the ground, most pavement conditions are okay. Whereas some other systems where they're pinned, they will need a reasonable pavement or a reasonable foundation to hold it in place. So we even detail the pavement, the foundation pavement conditions. Alrighty, a couple of terms that I probably went through there right at the end were working width and deflection. I think I do have a diagram in the next one to go through that. But I guess just to quickly clarify on this, deflection here is how far the vehicle and barrier, deflection is how far the barrier has moved or the cable has moved or the rail has moved during that impact. And the working width is how far either the barrier or the vehicle has moved or has extruded into during that impact. Most of the time, we look at MASH TL3, the deflection is very similar to the working width. And that's because there's very little roll. The vehicle doesn't lean. And so you end up getting a deflection that's almost identical to the working width. Whereas once we start testing higher or taller vehicles, we will get a difference. The barrier cables might be down around the bottom of the vehicle at the wheel, whereas the actual vehicle itself is leaning beyond those cables, and we do get a slightly different working width and dynamic deflection.
So, Evan, questions coming from Mark. Is there any vehicle technology emerging to tackle post-impact trajectory, something like locking the wheel upon impact or those sorts of things? You heard of anything in that space?
I haven't actually. A lot of the discussions have been more about how do we set these barriers up to, I guess, talk to the vehicle or for the vehicle to be able to detect and avoid the impact, and other technology about how do we communicate when a barrier is being impacted. But no, I haven't actually heard about a technology to treat that. A lot of the road authorities have started talking to these the manufacturers of autonomous vehicles and are working through some of those challenges out on the network. So that might be an interesting one to sort of talk through is if it does happen, yes, we're doing everything we can to try and avoid a crash. But if it does, how do we best endure the crash? And it could be the same with lots of different furniture. So yeah, good question, but I don't have an answer, sorry.
While we're having questions there, Mark asked yesterday about network road risk intervention thresholds and the activity going on around different jurisdictions. Do you have any updates on anything going on there?
Yeah, so we did share kind of notes at the last ASBAP. While the people on that group aren't necessarily the ones developing those thresholds, we sort of do get involved in part 6, and so we did have a chat about it. From what I could see, Queensland had done the most pre-work, though they hadn't yet released the final report, but they were sort of on the track to hoping for a sort of a one value to rule sort of all of their network. Otherwise, WA, Western Australia, has got a group, and they're saying, right, that task is to try and set the thresholds for them. So they're currently analysing their roads, and they're using sort of the data that they've got. And similar, I guess, Victoria and RMS was similar in the fact that not specifically a group looking at it, but the conversations are being had with the various players around regions. How will a region set it versus a major project versus an urban? And I guess the big challenge is, how does the road authority choose to break up the network? Do you set one value for all roads, or do you allow various regions or various types of roads to have their own risk threshold? I don't think anyone's super close to releasing a value just yet. But I guess the most important thing is really getting your head around what you'll do with the value. Because in truth, we'll set a value and likely we'll change it. More information will become available and will change that specific value. But I think that the way you use that value is going to be very similar, whether we set 1.5 or 1.2 or 0.9, whatever. I think it's still understanding, well, what do I do with that value? How do I assess, my project? How do I identify the sections of road that are exceeding that threshold? And some projects that we've been working on down here in Victoria are kind of trying to set their own threshold to just say, look, we want to adopt the new Part 6. We've looked at our typical cross sections for the project, and we're proposing a value, and we sort of have that discussion with them so that they can work through that. But yeah, no one that I know of is they're ready to go.
Yeah, no, I think there's a fair bit of work to be done in the space of getting to the point where you've worked out how that plays out, and then getting that knowledge out to all the practitioners who are making then those on-ground project decisions.
Yeah.
So still a fair way to go. Good. All right. No other immediate questions have popped in. I might pop up a little poll, just a little bit of something. A few acronym challenges, and while you switch over slides, and I'll also give 2 minutes in there just for a stretch and fill up a water for everybody. We're just a bit under halfway through today's session, so I'm just going to get a poll up and running. And remember, everybody, you're not marked on this one. These are just for a bit of fun, really, a bit of checking that you're paying attention, but we don't take individual marks on this, but you might get something similar in your quiz. So pop some answers in there, have a stretch, and get get yourself a water or coffee or something, and we'll be back in 2.5 minutes. And there's 2 questions there for those, yes, seeing them.
Oh, I feel like that. The one person that got the ASBAP acronym, that was a nice close one. I feel I probably would have misread that one and gone with Austrode's standard barrier assessment of products.
Yes, yes. No, some tricky wording in there. They haven't quite seen this yet, Evan, though. So you and I are just the only ones that can see it.
Sorry.
It's all for a bit of fun anyway. And we've got how many? 12, 13. A few more who are scratching their head at exactly those sorts of things. And yes, have a stretch, and we'll get back into it very shortly. And you can load up your next presentation there, Evan. And
all right. Oh, I thought I had it. Yep. Oh, what's going on?
I think that's the one we just
Yeah.
finished.
Let me just minimize it.
That's the one. All right, we'll end the polling and share the results. And yep, most everybody was on it. I managed to trick a couple of people there just on some things that sound like they could be right, but technical conditions of use, as Evan mentioned, and the Austrode Safety Barrier Assessment Panel. I popped in there the Austrode Safety Standard Barrier Assessment of Products, which is, yeah. All right. Please keep your questions coming in the Q&A. Evan's got a wealth of knowledge to share, so if you do have questions to pop up, put them in there. Don't wait for a break to write them in. Just write them in as you think of them, and we'll get to them. But I'll let you keep moving along with permanent safety barrier products, Evan.
No worries. Thank you, Ken. So in this session, I just want to go through the general categories of permanent safety barriers. Now, I'm not going to go through specific deflections and working lengths and minimum lengths. That's, I guess, what the TCUs are for. Let me skip through some of this. Oops. But I want to sort of go through, the general pros and cons and unique characteristics of each of the different barrier types. And really just to get you guys familiar with the types so that it's a much easier process to go away. You'll see them in the accepted list. You can pull up the TCUs that give the certain values. But, you kind of know generally how they work. So I had structured this off one of our own. Whoops. I threw my mouse across the screen there. I have structured this similar to our list of safety barriers. So generally going through sort of flexible, semi-rigid, terminals, and then into some of the unique and permanent concrete. But like I showed before, RMS does split their documents slightly differently, but nonetheless, the specific products are the same. So the first thing I wanted to talk about, proprietary versus public domain. Now, these terms refer, or proprietary products infer that there's intellectual property. So a supplier, a company has invested the money, they've designed the product, they've crash tested it, and as such, it must be purchased from them. Public domain, on the other hand, implies that anyone can manufacture it as long as they manufacture it to the right standard. And a classic example of public domain would be your G4 guard fence. You know, it was crash tested, it was designed by a road authority, and therefore the road authority really just gives the details and says G4 is accepted, here's how you manufacture it, here's how you install it. And anyone that can achieve that, anyone that can manufacture it can do so. In the last 10 years, we are shifting much more to proprietary systems because they can develop that business case. They can actually show the investment and they'll push innovation much faster than public domain can, given we need to put sort of a business case and convince the road authority that it's worth it. But I will try and highlight which ones are proprietary and which ones are public domain. So wire rope, first cab off the rank. I wanted to go through the general components of each of them. Each wire rope product has concrete foundations. Now the sizes might be slightly different. Most of them I think are about the same. 300 mils diameter, 600 mils deep. They then each have a plastic sleeve that gets pushed into the concrete foundation after it's just been poured. They then have a steel post that slots into that. So there's nothing really holding it down. It just falls down into the post sleeve. And the shape of this post is slightly different, but generally around the same, 150, 200 mils wide. And there's generally got slots for the cable. Then there's the ropes. All the ropes are pretty much exactly the same. For each of the wire rope systems, it's just how they connect or how they weave around the posts. They all then have a terminal and a ground block. So the anchor block, very important, holds that cable down during an impact. The way that they transition down is slightly different. We used to have no posts, which was not good. We've gone back and then they figured out how to achieve that. So there's generally either a couple or an array of posts that reduce in size. But generally a wire rope system looks something like that. The point I like to make from this video is that the posts aren't there just to hold up the cables. They're there to hold up the cables and provide downstream and upstream resistance. So if I pause it there, you can see that these posts downstream are bending when there's enough pressure, and these ones are holding. And so the strength of the post and how hard or how long it holds that cable is very, very important because it holds the cable tight against the vehicle. Now, as the vehicle, pushes and gets closer, eventually these posts will bend, but well before the actual vehicle gets there. And so with this in mind, the more posts, the stronger the resistance because there's more, posts to pull over as the cable deflects. Less posts means that there's far less resistance on the cable. The barrier would deflect quite a lot and potentially the cables would even drop down or come over the top of the vehicle because there's no posts holding the cables in place. So, there is some theory going around, you could just make the posts out of anything. They don't do anything but hold up the cables. Entirely incorrect. And the strength and how long they hold those cables before they release is pretty much what makes up the cable, and as such is what makes up the IP. It's all around that sort of post interaction with the cable. The cable you can just get from anywhere. It's all around that post. Now we've moved from 350. So I only wanted to introduce some of the new MASH wire rope systems. We currently have 3 MASH wire rope systems. The suppliers are the same as before. They've got their same sort of companies over in America and Europe. Bryphon MASH. So this one is from Safe Direction. Again, we've got a round post and we've got a bit of a weave. We've got the Centuryline M, a MASH wire rope from ACP. Looks kind of similar to beforehand, with the clips or the arms on the outside that hold the cables, with one sliding down the middle. And the last, MASH Flex. So that's the old Flex fence, now called MASH Flex from Ingel. Their post does look very similar. However, they've taken on board some of the comments around how long it takes to add in each of the spaces, and they've integrated a post cap as one unit, which acts as the spacer. So they're trying to save some time in installation. But each of these are MASH tested and approved. The only one currently that is TL4 is actually the Centuryline M. Now, I'd imagine each of the others have plans and submitting those, but right now the Centuryline M is the only MASH TL4, but all are MASH TL3. Benefits of wire rope and limitations, very similar to beforehand. They are the most forgiving. Occupant risk values are the lowest, not the only ones that are below the limit, they're just the lowest. You can get quite high containment. So one of those, Centuryline M, TL4, but they do have this extra capacity. The cables can take quite a large energy or impact force before they got ever close to snapping, which means that we've had lots of scenarios around Australia where very big vehicles have impacted, the cables have engaged, and while there's lots more deflection, they were able to actually redirect that vehicle. So one of the benefits is this higher containment, even sort of the 3 to 4 and a little bit more. Low installation cost, low repair cost, narrow system width. Now, I will distinguish low repair cost, I guess, from low routine maintenance cost. Unfortunately, the cable barriers will require visual inspections to make sure the cable's not sagging, to make sure that the tension is where we want it to be. So you're kind of saying it's low installation, low repair cost, but unfortunately does require that extra inspection. Other limitations of wire rope, larger deflection area. So most forgiving, but you need the most room behind it. Deflection factors are required. So the longer you make the barrier, the more it will deflect. This is a big one, 200-meter radius. We can't put wire rope on curves any tighter than this, because on a cold day, when the tension of the cable increases a little bit, it can pull over some of those posts. So 200-meter radius is the minimum. If you need to go below that, or you have curves that are less than 200, you'll need to consider a guard fence or something else. And another one, I guess, not directly, you cannot be connected to other systems. So, if you've got a route and you've got a bridge barrier, or you've got a bridge on there, or you've got an abutment, and you're going to have to be swapping between barriers, wire rope needs to stand on its own. It can't be connected to anything, which means you may have a gap, or you may need to add an additional terminal or something. So again, the connections, what these systems can be transitioned to, is either a benefit or a limitation. In this case, I've put it in the limitation. Alrighty, next category, flexible guard fence. These terms, we've called it flexible guard fence down in Victoria. The other common term, weak post guard fence or weak post W-beam. The reason for the weak post, not that it it would yield if you kicked it or tried to push it. It's actually still quite strong, but it's the way that it behaves. And when the vehicle itself hits the post, it will bend. And the idea is that it bends and the W-beam releases from the post, and the W-beam stays at the right height, while the post bends over. And similar with the wire rope, same behavior. The post of the wire rope will bend when it's directly impacted. The cables will release, and the cables will sort of stay up here next to the barrier, or to the vehicle, until it gets redirected. Obviously, the posts up and downstream will add that resistance, but we call it weak post because it's not, each individual post is not directly resisting the impact load. It's kind of acting as a ribbon. The systems that fall into this category for W-beam, we've got the same three suppliers: INGAL, Safe Direction, and ACP. And that's these images over here on the right. The W-beam, so the rail here, and I'm calling it a W-beam because you can see there's kind of 1, 2 in the shape of a W. That's exactly the same for each of them. 2 meter long W-beam rail, can be manufactured anywhere. The IP and the value of all of these is in the post and the release mechanism. Does it release from the post, when it needs to, so that it stays up against the vehicle? And that's where there's the slight differences. We have a slider bracket here for one. We have a washer that's designed to pull through for the other. And the third has a weaker tab around it. So these are the important bits of the W-beam. I have chucked these ones in flexible. Again, I guess they're stronger posts, but they don't have the traditional block out. The Thri-beam rails, so EasyGuard HC and Sentry. I think it's actually called Sentry TL4. I might change that, but either way, these are both Thri-beam. So W-beam would just be the top two. This one adds that extra width or sort of height of the rail. Means that it can contain a larger impact load. And there's two current systems that are both MASH TL4, EasyGuard HC and Sentry TL4. So just having a quick look now, from what I've explained, you're going to quickly see these posts, because they're being directly impacted, likely to bend over straight away and release from the rail. We don't want to pull the rail down so that the vehicle comes straight over. We need to release from it. And then you'll sort of see these holding up until the vehicle eventually gets to these. And the W-beam hopefully staying along the edge and engaged with the vehicle the whole time. And so that's what we can see. The posts are bending. I go back. The posts directly bend over. The W-beam releases from the post, stays with the vehicle until the energy has been redirected. Different angle. Again, seeing the post pull over, releasing as they go, and the vehicle, the W-beam staying, engaged well with the vehicle. Useful place for W-beam barriers. Yes, that is a useful place. You've got these, rural or mountainous roads where you've got lots of curves. Yes, it can go around tighter curves. But I guess also, quite useful in the constrained locations. You've got a bit less deflection than wire rope. You've got no factors. You can make this as long as you need and the deflection won't change. Obviously, you need to consider access and having emergency brakes, but in theory you can have it as long as you need. Tight curves, damage is localized, so the barrier, there's no tension to be affected. It's just going to be the W-beam systems, in that spot that will need replacement. And then the other two that a key here, transition to other barriers. So you could directly connect to a Thri-beam, back down to W-beam, onto a concrete barrier, so you can create that consistency. And the other thing, motorcycle rub rails, these systems each have a rub rail that goes underneath that has been tested and designed to redirect a sliding motorcyclist. Unfortunately, we don't have any products like that for wire rope, but also wire rope's less likely to be in the locations where motorcyclists are coming off on tight curves and sliding. So again, a really big benefit of these systems. And if you do have, roads that have a high risk of motorcyclists leaving the road, then these flexible guard fence systems are definitely the better choice. Look, the main limitations, still fairly large deflections. And containment levels, I mean, now that we've got some of the Thri-beam systems, that's probably over here in the benefits. I guess they're slightly more expensive than wire rope, given you've just got a bit more steel in them. But still, you can get some fairly large containment levels now, which is good. The semi-rigid barriers, or commonly called strong post, the main difference being that each post will resist that impact. If the vehicle comes in right here, it's not plowing over this post. This post will resist for quite a bit longer to a much higher load limit until it begins to bend. And so the types of products that fit within this category are your G4 barrier, which is here behind the curve. This is type B down in Victoria. Your roller barrier, again, still some deflection, but we've got these posts and a rail connecting each of the posts. And if a vehicle hits, there'll be only a little bit of a deflection, but, it is still considered a strong post system. And this is the old T39, which I know we removed in Victoria, but I can't remember if other states, but I know there is definitely the G4 modified, or is it G9 modified, which is the Thri-beam strong post with quite a large block out on that. So that would also be considered a semi-rigid or a strong post system. Why use these? Lower deflection. We can protect hazards with much less room. Suitable for constrained locations. You can get higher containment out of these. So MASH TL4 for the roller barrier. And ultimately, whole of life may be greater. If they're in a location that's going to get hit more often, well, they're more likely to resist that impact and not require repair after every single nuisance impact or even normal impact. So again, you start to look at these when you are in a constrained location where you really need to squeeze something in. Okay, they're not as forgiving as flexible barriers, but they're still well below the preferred limits for deceleration. So, your real limits are greater cost and less forgiving, but very suitable for constrained locations.
Evan, we had a question in about the roller barrier, and do you know where it's been installed in Victoria or New South Wales?
Yep. So 2 installations down here in Victoria, and both have the same characteristic, an off-ramp and an on-ramp, both with very tight curves. So the off-ramp was the first location, very tight spot with residential properties around. Ideally, you would extend the off-ramp, change the radii to make it more gradual. But the reality was people are over, coming in too fast. And so we installed the roller barrier to try and get them back on track. And, it has been hit numerous times and seems to be doing a very good job. Obviously, in that location, it's paid for itself in the fact that our maintenance team aren't out there every second weekend fixing it.
That's not in Point Cook, is it?
That's the Point Cook one. And then the second one, Green Gully Road, is on an on-ramp, there's a tight curve, which people also take fairly fast around the curve and onto the on-ramp. And again, that was the second location that we've installed it. I believe WA may have one location. But yeah, look, what can I say? It is a good product. It does cost more than others, which means that, it's generally being dismissed, earlier days. But for those sorts of locations, the delineation that it provides, the sort of resistance to the nuisance impacts has actually made it very successful in the 2 locations we've got. I don't think it's the sort of product that you just choose as your longitudinal barrier for the whole route. But, if you do have some sort of unique sites where it's just, not possible to realign the road, then, it has proven to be a fairly good product.
Okay, thank you.
A couple of just little variants that I wanted to mention, which are common with all of these systems. Some have been tested, some have been simulated, and others were kind of just accepted, a while ago, based on sort of theoretical. Post spacing, base plates, post emission, double blockouts, and double nesting. I think I've got an image for each of these. So I skipped post spacing. So one, post spacing. Most of these systems are tested at one post spacing, and therefore you use it at that. For guard fence, it's 2 meters. All of them are pretty much 2 meter post spacings. For wire rope, though, it kind of varies between 2.5 and 3. Again, the supplier has this tough decision of, do I want to be the cheapest product, which means less posts, or the product with the least deflection, which means more posts? And so some of them have crash tested with different post spacings. In Victoria, we've tried to harmonize that by just adopting a 2 meter and a 3 meter post spacing, just for simplicity. And it's easier to specify just wire rope on the plans rather than having to specify one specific product. But yeah, post spacings can be varied, and you can reduce your post spacing for short sections to get, past a hazard that's really close to the road. Generally, you want to use the post spacing that was tested, but reducing the post spacing is useful in constrained locations. The second one there, post types. So most posts are just driven. We do have different variants. This is a base plated post that goes onto a concrete foundation, useful for over a culvert or over a service. And a lot of these variants are being submitted. So a lot of the products are just, variants are being added to the TCU. So if I pulled up the EasyGuard or Safe Directions Ram Shield, it would have these on there. The other one that's popping up, post emission. Basically the idea of leaving out a post to span a hazard, culvert, service, whatever. This one's actually the Ram Shield, and they tested 2 posts missing. They basically move the post over to here in between the other 2, so they make it a bit stiffer at each end, but it allows them to get a 6 meter span. So again, quite useful. And this other thing, the Abraham block and the Easy Lift. So some systems have acknowledged that over time we add overlays. We do add different treatments to our pavement. And so to make sure that we can adjust the height of the barrier to match that, because you don't want your barrier being installed and then all the vehicles essentially being lifted up so they hit higher on the barrier. We have sort of the Abraham block, which can be attached to some of our public domain guard fence, and some of the suppliers like EasyGuard have added this Easy Lift. In the case of Ram Shield, they just simulated at all different heights. So they've basically proven that their typical installation height is actually quite high, but it still works. And therefore you can adjust it a certain amount before it begins to fall out of tolerance. So they sort of went that opposite direction to adding an actual physical change to the barrier. Alrighty, let's keep moving. Terminals. Wire rope terminals, there is really not much to say about them. They essentially go from the full height post down to the anchor. The amount of posts, the height and angle all kind of depends on the specific product. They have been crash tested, head on, and I mean, yes, the vehicle ramps up. There's no real other way to kind of do it. But it's all about these posts breaking over and, the vehicle eventually comes to a stop. If you do hit right at the angle, you'll go straight through because it's a gating system. But otherwise, if you hit at an angle or head on, you're not really losing that much speed. It's just been tested and proven that it doesn't create a hazard for the driver. Guard fence terminals. So the images I've got there are the MASH terminals. So we've got the MSKT, safe direction, the ETSS, this one, and then the max tensions are the same suppliers again, Ingal, safe direction, ACP. The value of these over the wire rope is they actually absorb energy. Which again, if someone's running off the road and hitting the terminal, it is, sort of nice to know that you've actually brought them to a stop before they've progressed beyond. And, some of them do have some shorter length versions for TL2, 70 Ks versus 100 Ks. So they're essentially one for each of the guard fence systems. The two bits that I wanted to get into are how they work. One is called an extruder terminal. So that's the MSKT. And then the other two are called tension systems. And the way to tell the difference is here. There's, you can see a cable hanging out the front, and same again. This one doesn't. It's just got this, the head unit sitting out and over the first terminal. And I'll explain what the differences are. The extruder system, the MSKT, these gray lines represent the W-beam, the rail, and during installation, you place this terminal head onto the end of the first W-beam system. When someone comes along and impacts it, it slides along the W-beam and it pushes it through this tight little width. And basically that absorbs energy. And so by the time you've pushed it through all the way through the sort of first three rails, it's shot out, it's absorbed energy via friction. And by the time you sort of get to the full length of the system, you've absorbed enough energy to bring a pickup truck to a stop. I do have sort of an example of one fully impacted and redirected. Obviously this W-beam was all straight and it's shot out the end of it here. Which means that the most critical thing with the extruder terminal is getting this terminal head onto the end of the W-beam. If you ever see a W-beam sort of sitting out or not sitting inside the terminal head, then it's not going to extrude. It's not going to push the W-beam through the terminal head. The other version is called the tension system. And basically this has some form of continuous unit, whether that's a cable, whether that's the W-beam itself. It's anchored at, it's anchored at a post that's actually further forward than the head that you see. The cable anchors itself there and runs through the terminal head so that when it gets impacted, the terminal head actually holds onto this and sort of pulls along, and by doing that absorbs the energy through friction again. The W-beams generally concertina over each other, so you end up with sort of a couple stacked on top of each other after a big impact. But the key is that remains taut, and that terminal head is sort of pulled along all the way from where it was, here, pulled along and absorbed energy until it finally gets to its to its end. Again, the most important thing here, one, that the cables are actually anchored and they don't pull out during an impact. And two, that there is a locking system here. And to make sure that these systems are actually taut and are actually grabbing onto the cable so that it absorbs friction during an impact. I think I've got a video of one of the older products, the T2000. Again, you see the vehicle come in and it shoots out of that terminal. So it's sitting on the top here, and then as it pushes out, it's going to send it out. Eventually, the amount of energy needed to push through will be less than what the vehicle's providing, and so the vehicle will sort of come to a stop and rotate out of the way. Crash cushions at 10:30. Again, we've got several MASH crash cushions. QuadGuard M10, Smart, Tau M, and Hercules. I think in this order, QuadGuard M10, that's the Tau, so that's the Smart, that's the Hercules. Sorry, that was a confusing way to do it. The benefit of these are they're standalone. They're crash tested to 100 Ks. You can make them longer for greater speeds. They can sit on the end of a rigid barrier. They're quite short in terms of things. For 100 Ks, you only need around 9 meters. Versus a guard fence, you would need the terminal, 16 meters plus a transition to get to concrete. You could put these on the end of a pier or, sort of a hazard. So they are quite versatile and do perform very, very well. The downside is they're quite expensive. And so really we'll be using them for, places that get impacted a lot, gore areas, off ramps, highways, or just really constrained locations where we couldn't get a normal barrier in. I think I've got a few photos coming up, but here's a photo or a video of one. And, just to show 100 Ks an hour, 2-ton vehicle, it is a quite good, impact. The occupant values obviously recorded and they are below the maximum limits. But yeah, just goes to show, sort of that's how they concertina over the cartridges inside will absorb the energy as they break. And so most systems have cartridges in each of the units, and they will crush and they will absorb energy. The other option is this hydraulic piston system. So there's one product out there called the Smart Terminal. It's a bit more expensive than the others, but the value is that there's no cartridges. All of the energy absorption is done underneath, which means if you need to repair it, you're only replacing a couple of bolts and resetting it. Whereas if you need to repair a cartridge system, then you got to buy new cartridges each time that they are damaged. Here, some good examples of, just wouldn't have the room to be able to protect these hazards. And so crash cushions can be quite useful. Here is actually one of the photos of our first roller barrier with a smart cushion on the end. So this is an off-ramp. Yes, there's heaps of speed warning stuff up behind the camera, but it is quite a tight curve nonetheless. You can get some wide variants. Again, you just wouldn't have the room to extend this barrier, up into the gore section, into the area where you've got someone going straight and someone going off on a different path. So you can get wide variants. I might come back to short radius curves if we have time, other than to say I've got some photos in there about how they perform. It's best to talk to the road authority about when to use them. They're not the greatest products. They definitely don't work as well as your crash cushions or your terminals, but they are a necessary evil in examples like I've shown there. where the hazard is really severe. You don't want people going off that cliff. I guess I just wanted to sort of highlight that, these systems work by breaking and, almost creating a bit of a net or a capture area. So if you're using it to protect hazards that are right here, then you just haven't protected them whatsoever. But, if you have got sort of a cliff or hazards out here, then, that's the amount of room that you will need. Transitions, really mainly just going to talk about sort of guard fence onto concrete. The importance is to do it as per, most of these are actually public domain transitions. So as per the RMS standard drawings or the Victorian standard drawings, the idea is that you slowly stiffen the system. So you can see there the post spacings begin to increase, so that you're going from, a deflection of 1 to 1.5 down to sort of less than 1, much lower, until you get into the sort of the rigid concrete barrier. None of the suppliers have really crash tested transitions other than the reverse impacts into their terminals. So the transitions are mostly public domain. Yes, the suppliers might produce a drawing just for ease, but that drawing is typically based on the public domain transition. Again, shows sort of the purpose to redirect vehicles away from that rigid end. And there is a new transition coming soon. There's going to be a webinar from Austroads, I think early Feb. They haven't sent out any details yet, but that's currently the plan. And they'll go through sort of a new Austroads transition that includes a thry beam onto a concrete, whether it's F-shape or single slope or whatever. And this will be the transition that most of the road authorities will be adopting after that. Definitely true in Victoria, currently working on the standard drawings for it, which will mean, whether it's W-beam, you have to transition down, or if it's thry beam, you just connect straight onto it. These unique products, Raptor, energy absorbing bollard, they are accepted in Victoria. They are on the list. And I think RMS definitely have the Raptor. At 50, they don't have the energy absorbing bollard because it just haven't passed the crash testing. These are, again, 4 unique situations. The Raptor up the top, basically designed to be a giant plastic crash cushion. If you hit it, it spreads the load, it absorbs some energy. It's better than hitting the pole. But again, it's far less effective than an actual barrier that redirects the energy. So in Victoria, they're by exception only. You need to be proving that the pole actually has a risk and that nothing else could actually be achieved. And that means a non-conforming barrier is being considered before a Raptor. I want to see that a barrier couldn't go in even if you couldn't achieve the deflection or the length before just resorting to a Raptor, because there's still just apple and oranges. A non-conforming barrier might still have better performance than a Raptor. Similarly, energy absorbing bollards, they're pretty much just rigid impacts. They do have some value in the fact that they'll bend and they convert the energy to an upwards momentum, meaning that the vehicle runs up, doesn't transfer as much load to the occupant. We use them for protecting vulnerable road users. So tram stops, dining areas, local urban roads. What we don't really promote them for is just protecting other hazards, like using a pole, an energy absorbing bollard to protect a pole or a tree. You're really just kind of replacing it with the same sort of hazard. But for these urban environments, they can be very useful because at least we know the vehicle's been stopped before they hit someone. Photo of a Raptor. Concrete barriers, quickly touch on, and then I better finish up this session. We don't have off-the-shelf concrete barriers. There are some temporary ones off the shelf, but when we're talking about permanent concrete barriers, they need to be designed for the site. Now, there might be a nominal installation where everything, if you can achieve everything correctly, then you can sort of install per the standard drawing. But generally, we're looking for sorts of, several things. The shape, in Victoria, we use F shape and so does RMS. Queensland use constant slope, WA use F shape, but shape is very important because that's how it redirects and sort of absorbs the energy of the small car. Height is critical. 820 for TL3, 920 for TL4, and 1100 for TL5. Obviously, those are the minimum heights. Taller barriers would be better, but those are the minimum heights to achieve the new MASH test levels. And then essentially that the whole system acts and is anchored such that it can redirect a vehicle. The combination of reinforcement, whether that's longitudinal bars or a cage, connections, making sure each unit is connected to the next. So whether it's a precast system or a slip form, those connections will vary. The anchorage, how is it embedded? How deep is the embedment? What's the support on the surrounds? If this is a verge, how high does the soil get placed up behind the barrier? And terminals, making sure that the end of the system is anchored and there's generally a larger terminal or foundation for the concrete. And so basically, this is kind of split up into various standard drawings. Some show you the shape and the height. Some show you the standard depth for embedment. But generally, the designer will have to take that away and design the concrete barriers specifically for their site. F shape, why do we call it F shape? Well, they tested shape A, B, C, D, E, and F had the lowest occupant risk values for the small car. And so F shape, and you can see slight differences in angles and widths and everything. F shape was the preferred. So kind of looks exactly the same to New Jersey shape that everyone mentions, but they are slightly different. Showing a bit of installation. For bridges, similar components, still the right shape, still the right height, but you also have to meet certain design loads, durability, 100-year design life, etc. Designing a barrier for a bridge is much more time consuming, and the product will generally be more expensive because it's going on to a bridge, it's connected to the deck. It needs to meet AS 5100. So it is sort of important to identify where you need a bridge barrier and make sure you talk to a structural designer. But AS 5100 is sort of your key reference for that. There is some equivalence because they're based on the same crash tests, and that's generally the approach. But it is kind of important to note that while they're based on the same impacts, providing a wire rope on a bridge doesn't meet AS 5100. It doesn't have a design life of 100 years. It doesn't have all the requirements of AS 5100. And so, I guess it's just important to know while they are, equivalent at a base, they're not, I guess, alternatives to each other. I would highly recommend, not thinking you can use a roadside barrier on a bridge because you're most likely to get turned down. And here's just several photos of different sort of shapes and designs within Victoria.
Okay, no questions have come in at this stage, Evan, so you can tick over to your final presentation. But in the Q&A, somebody's kindly popped up the other roller barrier site there, the one in Keilor or Green Gully. So I think everybody can see that in the Q&A, so you can click on that link and have a look at the Street View. So thank you to whoever uploaded that.
Yes.
Back to you, Evan.
All righty. Look, I know I powered through that, but that was permanent products. Wire rope, guard fence, the terminals, crash cushions, and a bit of concrete at the end. Noting that, sort of roadside concrete is very different to the on structure concrete. The last category, and this is my last bit, which I'll try to squeeze in, is temporary barrier systems. Again, I won't go into the specific deflections and working widths and differences, but I just want to sort of talk about each of the categories in general. So we've got the concrete barriers very much, the way you design them, the way you test them, the way they're set up on site are exactly the same as permanent. The barrier systems will need a deflection area, space to move, to deflect, and you want to have your work area just like you would normally have your hazard outside that zone. So all the crash testing and everything is essentially exactly the same. When it comes to temporary, there's 4 general types. Concrete, pure concrete, generally with some reinforcement. Steel, pure steel, so generally a hollow shell, and I'll get into those. Composite, that's a mixture of steel shell with concrete ballast for a bit of extra weight, and water-filled plastic. So generally plastic without any water would just be a delineation device. The only way it comes in as a temporary barrier is if it is actually a water-filled plastic barrier. But those are the 4 categories, and there's sort of several products in each, though quite similar. Precast concrete. So couple of variants, T-Lock, JJ, which you can see up here, and the DB80. Generally, the actual concrete units are quite similar, F-shape, roughly 6 meters long, sometimes 3.6 meters. And it's really the connection that kind of separates each of them. The connection also can determine how much you can bend it around corners. And here lies the challenge with concrete. The harder or the tighter that connection is, the less the system's going to deflect, because the whole system will slide and deflect as one unit, and there won't be any bending in between units. However, the tighter you make that connection, the less you can actually bend it out on site. So again, there's this real challenge for manufacturers or suppliers. Am I the system that has the least deflection, or am I the system that's the most usable out on site? And unfortunately, most people look at the TCUs and go, yep, I'll take the least deflection. They'll buy these systems, and then they'll get out on site and go, wait a second, I can't bend it around the site I've got. So just a note that there's always some pros and cons into each of these products. Steel, much lighter than concrete, much more durable than concrete, but because there's no weight to them, they need to be pinned. The concrete barriers I showed before are freestanding, except at the terminals. All steel barriers must be pinned. Now, how often you pin them will basically depend on how much deflection you need. 60 meters is a common pin spacing that will get you the most deflection. 12 meters, lower deflection, and 6 meters, which is essentially each unit minimum deflection. And most of these products each have that sort of variant. They'll have a standard, they'll have a LDS, a low deflection system, and they'll have an MDS, a minimum deflection system. Obviously, the more rigid the system, the stiffer the system, the more likely a larger vehicle is going to hit it and tilt. So a lot of these systems can achieve MASH TL4 with a 60-meter post spacing because the whole barrier will deflect, the vehicle will remain stable. The more you pin it, the stiffer you make it, the more likely that vehicle is to tip over when it's hit. And so a lot of the minimum deflection systems are actually TL3, while the normal systems, it's the same unit. It's just how often you pin it. Will make it TL3 or 4, and so too will the deflection change. But again, we're talking about testing worst practical cases on many work sites. You'll have a combination of speed reductions. There won't be as many lanes, therefore the angle, won't be able to achieve sort of that 15 degrees. So again, there's lots of little factors that will mean, okay, we're using a minimum deflection system. We understand it's only TL3, whatever. That's sort of part of the selection and risk process. Composite, very similar to steel, but they'll have a concrete ballast on the inside. The value of these, or the benefit of these, is that 1, they're still durable. 2, they can be used pinned and freestanding because they've got the weight. You could use this unit in a freestanding configuration, or if you needed to pin it, you could come along and pin it 60 meters, 12 meters, or 6 meters. So that is the value of these composite products. The disbenefit is that they now weigh 600 kilograms again, so you lose some of that flexibility with being able to move them around on site and how much you can cut to the site in one go. So kind of a combination of the concrete and the steel. A couple of unique ones here. Mobile barrier systems, I don't really have any on the side, but just wanted to introduce that they are on the list. Fully crash tested, angle on, TMA on the back, can be used to sort of protect workers in a very short-term configuration. Plastic water filled, not much to really say. They have changed over the years in the fact that they've become taller. The plastic is a much higher quality. Some even have some steel cables running on the inside. But like all of them, like concrete, like steel, like plastic water filled, you need a continuous length. They all rely on the weight of the system, unless it's pinned, because then it's relying on the anchorage. If it's a freestanding system, and it relies on the weight. And so making sure each unit is connected is critical. Making sure that you've got enough weight as a whole system to get the deflection you need is also critical. And finally, the other critical thing here is to have the right units on the terminal. Some systems, well, they all pretty much use a different color for the terminals. Some units are actually identical, but they'll have holes in them so that you can't accidentally fill it with water. Whereas some others are quite different in the fact that there's no steel cables running up here, where there are steel cables running in the actual longitudinal barrier. So it is important to use the right terminal end, which will be in the product manual. That is a summary there, but a range of different test levels for each of them. The general gist, though, is your concrete and steel is 3, or concrete TL3, steel TL3 and 4, whereas plastic is really down to that TL1 and 2 for the lower speed environments. Terminals, I won't go into this. No. The different terminal types, your plastic gating terminals. So these can go on concrete, they can go on steel. You'll have to check the right technical conditions of use. But generally there's some sort of a connection. They are tested for this critical impact point. And I'm looking here at SLED, the Absorb 3, the Absorb M, So again, they are quite useful freestanding systems, so they don't need to be anchored to the ground. And then the other main category being crash cushions, exactly the same as the previous crash cushions. However, there's generally sort of a neater or more convenient way to anchor the system. For example, here they come on a steel plate, which means that you can anchor the plate itself to the foundation rather than having to get in and try and anchor all the relevant sections. So again, very similar to what I've been through with the permanent crash cushions. The value of these is that, on a high speed anchored system, that's pretty much your only option. The other thing, I guess, is on the reverse direction, it is critical to make sure that transition is correct. For a one-way road, okay, they've obviously just placed the crash cushion, overlapping the front of the concrete, which is fine for one-way traffic only. But the second you've got that possibility or that potential for a reverse angle, you need to make sure there's the right connection. And each of the systems will detail that. If the system doesn't have one of those connections, then we've tried to be clear in the TCUs that it shall only be used for one-way roads. We didn't want to exclude the fact that this works. For example, the crash cushion does work on this concrete barrier for a one-way road, so we might as well accept that. But we also wanted to highlight that this has definitely not been tested in the reverse direction. And so therefore, you must be putting a barrier in, or you must be trying to reduce that risk at all costs, where there are some products that can actually be connected. And I'm mainly thinking of steel products. Many of the steel barriers can be connected to crash cushions. Summary, foundation. Yep. If they're anchored, that's the key. Pin them correctly, anchor them correctly, because that's how they redirect the vehicle. If they're freestanding, make sure they're all connected together. Make sure you have a system length and weight. Otherwise, I think that's probably it for the summary. And if there's any last questions, otherwise I can give you back a few minutes. Ken, apologize for the exercise.
No, it's great, Evan. You've covered a huge amount, and people can go back to the recording if something they wanted to just recap or have a look at the notes that they have. There hasn't been any specific questions come in. I'll introduce the exercise, and if anybody does have a question in the last few minutes, we can take that. But you are going to be asked now to do a little assignment. It's not hard, and I'll just share my screen and show you what I've just emailed you. But you can also get it in Moodle, so you can pick it up there, no worries. But you'll see that you've been given a Word document that looks like this, and it's simply, you are going to fill out anything that's highlighted yellow, so your name, your jurisdiction, which is New South Wales from all of you, and then the product that you've been given. Now, you've each been assigned a product. It's in a PDF, and here it is. So you find that product, whichever it is, you type it into here, and then you just say, what is the status of that product in New South Wales? And so you would replace the text here with what is correct. What is the what test levels of the system? So it could be 1 or more. And then between 1 and 3 advantages of that product and 1 and 3 disadvantages of that product compared to like products. So that's going to really require you to go onto the Transport for New South Wales website, the RMS website, find the product, find the sheet, have a look at it, see what its status is, find out a bit of information about it, and then just fill that out. And then you'll upload that to Moodle. So as easy as that. And I've emailed you that, but also I have it's in Moodle, so you've got plenty of ways to find it. If you have any issues with this at all, get in contact with me. If you're struggling, let me know. It should be a fairly short exercise, 10 to 15 minutes really. If it's taking you a lot longer than that, you're doing too much in this one. You also have a quiz to do, yeah, I think that's about it. The notes and the videos of the sessions are available in Moodle, and we've got a 9 o'clock start tomorrow. Log in a little bit early, and you're a chance to win a prize in the quiz. So thank you very much for your time, Evan. Always great to have your expertise, and gee, you do cover a lot in the 2 hours, and it's fantastic. All right, thanks everybody.
All righty, see you guys.